Okay, so the only way that you can figure out the number of neutrons is by doing what? Because there's no number for neutrons on the periodic table. So what's the way that we do that? This is something that you guys should know. We've been talking about this on and off since the very beginning of school. Close your computer, Kate. Cole, sorry. Both of you. Is it a double? I meant Cole, but you had yours open for a while too. Okay. How do we find the number of neutrons?
Subtract the atomic number by the mass number.
Yeah, subtract the two, because this is protons and neutrons, and if you subtract the protons from that, you'd be left with neutrons. At this point, all of you should be able to like pull that up. That should not be shocking or unknown, okay? That's how we find the number of neutrons. There's no other way, right? The other thing that I want to make sure to point out is sometimes we name our isotopes, or we do name our isotopes by the mass number. So whatever the mass number is, we add that up, and that becomes how we name it. So hydrogen 1, hydrogen 2, hydrogen 3, lithium 7, lithium 6. We looked at carbon 12 and carbon 14. So if you see a number after the symbol, that's the mass number, and that can let you know how many neutrons you have. You could take your mass number from the atomic number for that element, subtract them to get your number of neutrons. Okay, so one thing that we've kind of hinted at, a couple of the videos have shown is, and this is our first slide for today, this is 19, is that when you have this unstable atom, right, it is going to emit radiation, right, as it's going through that decay process. It does this in the form of very fast moving particles with the energy to produce a new nucleus, therefore changing the identity of the original element. So sometimes the original element is called like the parent atom, and then the new element is like the daughter element, okay? So just kind of going along like with that parent-child idea, I don't know why they don't say a son, but just like when we looked at meiosis and mitosis last year, we have the parent cell and then the daughter cell, so it's kind of following that same line. Where you have the original element and then you have like what's created from that, and we call that the daughter. Okay. All right, so there's 3 types of particles that are released during radiation, and that one video yesterday got into very specifics. We are not going to get into the different types of alpha and beta particles. Just realize that there are 3. We have the alpha, the beta, and the gamma. And for what we need to know, we just need to realize that these are the least dangerous, and then these are the most dangerous, okay? So as we kind of go through. And so we don't need to get into the very specifics. That's for another class. Again, this is just an introduction. So these elements are actually undergoing nuclear radiation and are considered to be radioactive. So as an element is decaying, it is going to release one of these forms of radiation. Okay, so the alpha gets stopped at skin. The beta can go through tissue and skin, but it gets stopped at aluminum. The gamma, you can see move this way. They go through flesh, they go through aluminum, but they get stopped at lead. They also get stopped at like concrete. So, you know, there are materials that will stop the gamma rays. So we know like how to keep, you know, people safe, how to keep things contained, but understanding that the gamma are definitely the most penetrating, and they can be the most deadly.
Is there anything more that you know?
In terms of radiation, I don't believe so. I don't want to say 100% that, not that I'm aware of, Dylan. This is just another way to look at this. So if this is the radioactive source or the element, you can see the gamma rays can go through paper, they can go through aluminum, but then they get stopped at concrete. The beta rays can go through the paper but get stopped at aluminum, and then the alpha, they can't even go through the paper. Okay. So again, the different forms of radiation can cause different, levels of damage. So, you know, when they're going, like if you're talking about us, you know, what the problem is those gamma rays, they can go through, but they're disrupting cells. And if you disrupt enough cells, then you cause damage. So that's why radiation is used to target cancer cells, because obviously they're trying to kill those cancer cells. And so it has good uses, but then if not used carefully or used incorrectly, you know, it can cause some other problems. So have to be very, very careful with how that radiation is used. And so that's why usually the radiation is like very, very precise and very pinpointed to a target area where those cancer cells are, because obviously you don't want to damage surrounding cells that are healthy. So again, and that's really all I need you to know about radiation right now: alpha, beta, gamma, and then what's more, you know, like the gamma are the most deadly and dangerous, the alpha are the most safe and benign. Okay, so we're moving on to one of our big kind of ideas for this unit, and it's talking about half-life. Okay, so this is going to be a chance when we do our first set of kind of real calculations in this class. Right, so we have this radioactive decay and half-life, and this has also been talked about in some of the videos so far that we've had. But the half-life is the amount of time it takes for half of the atoms in a sample to decay. Well, that makes sense, right? So we can't pinpoint like when exactly an atom is going to decay, but we can kind of pinpoint when like a group of them will. So kind of like an average almost. And so the half-life for an element is going to be a constant. This is a characteristic that is unique to that specific element. Okay, so, you know, just like its atomic number and just like its mass number, those are specific characteristics for a unique element. Half-life is specific to an element also. So it's a constant, it's unique, and it does not depend on the number of atoms that are present. So you could have a whole bunch of them, or you could just have a few of them, and that half-life number is still always going to be the same. So there's a lot of different ways that we can approach this. And so we're going to go through quite a few examples so that you can see the different various ways that these questions might be asked and how we can kind of manipulate what we know to figure out what we're trying to find. Okay. The other thing that it does not depend on is how long it has been around. So it's not like it's going to go bad or that's going to change. And so these things make half-life a very, very useful tool for us. And so it's important to remember that we can't just consider like one single radioactive atom because that's not predictable, but a group of them is. So when you examine the half-life of an element, you're looking at a sample of that element that includes many atoms of that specific element. So if you look at this graph, and I'll step back for a second to make sure you can get the writing in, and we'll look at it. So typically this is going to be like looking at a sample. Okay, so here's our initial sample of radioactive material. And then the amount of time it takes for half of that sample to decay is our first half-life. And so if we looked at this, if it would tell us, you know, this took place at over 8 days. So the half-life for this sample or this type of element would be 8 days. Okay, and then for half of this sample that's left to decay is its second half-life. And then for half of that to decay is its third half-life. So if every half-life is 8 days, then another 8 days, the remaining half. And then the other 8 days, we get that cut in half again. So basically you're just cutting it in half, and 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 half, until finally you get down to where there's none left. Okay, but if the half-life is 8 days, then every half-life cycle is going to be a multiple of 8. So we have 8, 16, 24, 32, and you just keep going and going and going until there's none left. Okay, but you can visually see you have the full amount, now you have half, now you cut that half in half, now you cut that in half, this would get cut in half. So you keep cutting it in half, and then finally, you get to the end. Okay, so the half-life is gonna be the time it takes for half of that sample to decay. So it does pretty much exactly what the name itself says. And if you just relate that to the sample decaying, it's the amount of time it takes for half of that sample to decay. And then whatever's left, that becomes kind of like your new hole, and that gets cut in half. And that becomes your new hole, and then that gets cut in half. Over and over and over. Okay, so for most problems, you're gonna need to determine how many half-life cycles a sample went through, and then use that information to answer the second part of the problem. So you have to do one step before you can get to the final step. So like I said, we're gonna look at quite a few of these problems. There's two different ways to determine how many half-life cycles a sample went through. So, for example, the problem might give you two time values. So you have a total amount of time and how long an isotope's half-life is. Or the problem might give you two sample amounts. One that the sample started at, the bigger one, and then one that the sample ended at. So if you have 100 grams and then you ended at 12 grams, okay? So it might give you two sample amounts, or you might be given two time amounts. And there's two different ways to approach it depending on how the problem is presented to you. All right, so here's the first practice problem. So barium-122 has a half-life of 2 minutes. You have a sample of 80 grams. After 10 minutes, how many half-lives have passed? So when I look at this, I see that I have, I'm given the half-life. I have a sample of 80 grams, and I want to know how many half-lives would have passed after 10 minutes. So here's how you go about it. Second part, and how much of the barium sample is left. All right, so here's what we're gonna do. We're gonna solve the first part of the equation first. That kind of makes sense. Next thing we're gonna do is ask ourselves, what do we see two of? All right, so do you see 2 times, or do you see 2 sample amounts? What do you see? 2 times, okay? We see 2 time values. I see 2 minutes and I see 10 minutes. So this is how you would go ahead with this type of problem if you're given 2 time values. All right, so again, this is just the problem. I just have it on every slide so that you have the problem right in front of you. So the first thing you're gonna do is take your total time. So what was the total time in this problem? How much time went by? Ethan's telling me 10, okay? So we had 10 minutes, and then what was the half-life that was given in this problem? It said it has half-life of 2. All right, so once you've determined that, you take your 10 minutes and divide it by your half-life of 2 minutes. And so you end up with 5 half-lives. Awesome. Not too bad, right? And you're always allowed to use a calculator. I don't have a problem with that. Okay, so that's your answer for part 1. Now, we have to remember to solve part 2. It wants to know how much barium a sample is left. So, we started with 80 grams. Half-life means you're cutting things in half. So this means you need to cut in half 5 times, because you take 80 and divide it in half. Then you take that number and divide it in half. And you have to do that a total of 5 times. You have to do 5 divisions if it went through 5 half-lives. okay? So, you have to cut or divide by 2 what was your total sample that you started with? 80 grams. And how many times are you gonna have to divide it in half? How many half-lives did it go through? 5. Okay? So we're gonna have to cut 80 in half 5 times. So I have it kind of broken down. So we have 80 grams divided by 2, because dividing by 2 is cutting it in half. You guys all agree with that? Okay, so 80 divided by 2 is gonna give us 40. I have to divide again by 2 to get 20. I have to divide again by 2 to get 10. I have to divide again by 2 to get 5, and divide again by 2 to get 2.5 grams. I'm gonna check myself, because this is where people sometimes they do one less than they should. Make sure you see 1, 2, 3, 4, 5 divisions. Okay, 5 times you cut it in half, because that would mean that you went through 5 half-life cycles. A lot of times people will leave it at that. Like they forget to do the final one. And I don't know why, but that happens a lot. Okay? So be sure that you have divided the sample in half 5 times. So it's easy to divide 1 too many or 1 too few. Usually it's 1 too few. But I have 1 division, 2 division, 3, 4, 5 times I cut it in half. Make sense? So again, when we do it in our notes, I break it down extremely detailed, right? And then when we get to our practice problems, hopefully if you need to look back at the steps, you can. But obviously you're not gonna have to write out all of this. You'll have to do this, but you're not gonna have to do these arrows and all that stuff. But our final answer is 2.5 grams of the barium is left after 10 minutes have gone by. And so this is an example if you're given 2 time values to start. The other way that you could approach this is if you're given another type of question. So this one is example number 2. It says phosphorus 32 is an isotope that has a half-life of 14 days. There is a sample of 64 grams of phosphorus that has decayed to 8 grams. How many half-life cycles has it gone through? All right, so second part is, and how much time did it take for this to happen? So the first thing you have to ask, well, first of all, we're gonna solve part 1. What do you see 2 of? Do you see 2 times or do you see 2 sample amounts? Caden, what do you see?
Sample amounts.
Yeah, 2 samples, good. I see 2 sample amounts. I see a 64 gram and I see an 8 gram. So that means we're going to have to set it up this way. Okay, so take your starting amount of phosphorus, so the big one. So what's our big amount? Selena, for this problem, what's the big amount? Is it 64 grams or 8 grams?
64.
Good, so the 64 grams is the bigger amount, and we're gonna cut it in half, which is dividing by 2, until you reach the smaller amount. And what's the smaller amount, Dylan?
Smaller amount?
In grams.
What are we dividing by 2?
We're dividing 64 by 2, but what's the
32.
what's the smaller amount that's given in the problem?
8 grams.
Good. So we're gonna have to go from 64 to 8. All right, and that's what you have to kind of keep in your mind first. You're going from 64 to 8. So not 64 divided by 8, but we're gonna have to take 64 and cut it in half, then take that answer and cut it in half, and keep doing that until we get to the answer of 8. So we start at 64.
You cut it in half 3 times.
Okay, let's see, hold on. So you're gonna end up with 8 grams after you started with 64. All right, so from here, we're gonna do the division. So 64 divided by 2 gives us 32. And then we have to divide it or cut it in half again.
16.
And then cut it in half again.
8.
Wait a minute, I don't know.
It's like that in our notes.
Is it?
Yeah.
Yeah. Okay, cross it out. We don't need cross out from here to here.
The answer's eight.
Yeah, so this,
Ignore that.
we don't need this one.
That's a glitch.
That is a glitch. Sorry, I made changes to the notes last year. This is the first time I've used this copy, so yeah, I need to fix that, sorry.
It's a good thing I play Minecraft, because you could do that in Minecraft by splitting a stack of 64 blocks.
Oh, that's
And
why
then
you did it so
doing
quick.
that, doing in Minecraft until you just get down to like 8.
Okay, well, yeah, that's, so you're cutting it in half? So you're doing the half-life when you're doing that. So yeah, from here to here,
Minecraft Half-Life.
cross this out. All right, so the 2 gram divided by 2 equals, cross that out, sorry. So when we look at this, oh gosh, it probably messed it all up. I even checked this like 3 times. Okay, so we count how many times we divided or cut the 64 grams in half until we reached 8. And so it was 1, 2, should have only been 3, right? So, man, that's a big mistake. Yeah. I don't know how I missed that.
Oh, you're gonna have to.
Yeah, so cross out the 4, right? I'm sorry. Do you have the 4 in there too? Okay. Dang it. All right, so 64 to 32 to 16, and we end up with our 8 grams. All right, so we did this a total of 3 times. 3 times. I will fix it for the next class, but you guys are my unfortunate guinea pigs. And so it took 3 half-life cycles to go from 64 to 8. So again, 3 and 3, not 4 and 4.
How many times did this get messed up?
Everybody got the messed up version but you're the first ones that I caught it with, because you're my first class.
Okay.
Okay, so from here, our answer is 3, but we have to go back and do part 2, right? How much time did it take for this to happen? So going with our 3, not 4 answer, think about what we know. Well, we know that the phosphorus went through 3 half-life cycles, right? That's what we just solved. Went through those 3, not 4. So each cycle, and I'm glad you guys are here to like double check me, because I'd be thinking, am I really looking at this right?
You are trusting.
And it said in the problem, each half-life is 14 days, right? It says that right there in the problem. So if we went through 14, then another 14, and then another 14, or basically 14 times 3, that's how many, again, 3 cycles of 14 days each. And so basically we just multiply that. So 14 times 3, 3 half-lives times 14 days is going to give us 56 days. So it took a total of 42 days, thank you. It took us a total of 42 days. So again, I apologize. This is 3, this is 3, this is 3, and this is 42?
Yeah, we're really gonna have to fix that.
I'm gonna fix it as soon as you guys leave. Okay. You think you were losing it?
Yeah, when I saw 56.
What am I looking at wrong? Okay. Whew. All right. Well, you guys are unfortunate guinea pigs.
Hopefully.
So
someday
again-
There's a better time than this.
Yes. Okay. Let's stop.
Yes.
That'll work. That'll work there, and we'll fix this up. Yeah.
That sure would be crazy.
That's like, wait,